Okay, we're now going to work on summary questions of 7.2. Question 1. An object of weight 6.2 newtons is acted on by a horizontal force of 3.8 newtons. Calculate the resultant of these two forces for part A, and part B, determine the magnitude and direction of a third force acting on the object for it to be in equilibrium. Okay, so part A. We have, let's draw a diagram in so we can see clearly what we're looking at. We are going to have two forces perpendicular to each other, 6.2 for this one and 3.8 newtons. Now the resultant is clearly going to be in this direction here, and we call that R. It's going to be at this angle here to the 3.8 of theta. Now we can use the same results or geometry we used for part 7.1 to say that using Pythagoras theorem, R is going to be equal to the square root of 3.8 squared plus 6.2 squared. And when we chuck the numbers into the calculator, we get out 7.3 newtons, which sounds about right. And we can say that theta will be equal to tan, so minus 1 of the opposite over the adjacent. Opposite in this case, if you imagine this line would be at this point of the triangle, that would be 6.2 over 3.8. When we put them into the calculator, we get 58.5 degrees. Part B, it says calculate the force that would be needed to keep these two forces in equilibrium. It will be a third force. In fact, we know the magnitude of the third force, because it must be equal and opposite to the resultant of these two forces. We've basically, excuse the cat, we've basically decided that these two forces would have a resultant in this direction of magnitude 7.3. To keep everything in the right place, these forces would have to be matched by a force in this direction of 7.3 to counteract this resultant. So we can imagine this third force up here. Now the question then asks what angle it would form, and well, this really is not a very objective point to answer here. If we consider it as the angle to the horizontal, well, simple angle rules will tell us that that is theta, and therefore it actually be 58.5 degrees again, because this angle will match this angle. Looking at the answer they ask for in the book, they're actually decided to change their point of reference, which I think is not ideal, but that's what they've done. And they're looking actually for this angle here. Well, that's simple enough to work out. We call it theta 2, and that will be 90 degrees minus our original theta, which will give us 31.5 degrees, because this right angle here will be 90, therefore 90 take away this bit must give you this bit. This is from the vertical narrative, the horizontal, which again I don't think works well, considering here we gave the answer to the horizontal, but that's just to explain why the book says 31.5 degrees. Question 2. A small object of weight 5.4 newtons is at rest on a rough slope. What is it? Which is at an angle of 30 degrees to the horizontal. Sketch a diagram to show the three forces acting on the object. Calculate the frictional force on the object, the support force from the slope on the object. So, question 2. We have a standard object on a slope to draw. So first of all we draw a slope, and then we can say there is an object on that slope. We have been told that the angle here is 30 degrees. That's big enough to see on the screen. And that we know there'll be three forces acting on it. Or first force, is always the simplest, will be the weight, which will be, in this case, 5.4 newtons. That was given to us. We know that there will be frictional force, which is going to be in the direction of the slope. And lastly, we know that there must be a third force. That friction, I should draw that actually for proper terms, I should draw that across the bottom of the object. We know that there will be a third force, which I tend to call the normal force, the book calls the support force, doesn't matter which way around you want to call it, and that will be perpendicular to the slope, which is why I call it the normal. It'll be perpendicular to the slope. There's our three forces. So that, in a sense, answers question question A. For part B, we're asked to do some calculations. So first we need the frictional force on the object. Okay. Now, how do we deal with this? Well, as I've said to people in the past with these questions, if I've attended any of my workshops on it, you're going to find that this is in essence the same as a GCSE type question, where a GCSE question, I'm going to draw it up here, we would normally get an object acted on by horizontal and vertical forces, and we have to decide which force wins out. So, if these two are equal, it doesn't move that way. If it's equal this way, it doesn't move that way. Or if there's a resultant, it will move either that way or that way, depending on the resultant. Simple as that. As we can see from A-level questions, same thing, only instead of always being like this, we can get an angle. Now what we need to do is convert this into its components, and then we go back to our X and Y direction. Then we're back to a GCSE question where we're just doing sums, add or take away. The question, and what really confuses people, is where to take the X and Y. We're used to standardly taking the X and Y sort of lined up with the weight like this, but that makes no sense here because we have two forces at right angles to each other. Now, if they're at right angles to each other already, then we don't need to do any calculations to work with them. If we consider this to be horizontal and this to be vertical, then all we have to do is change this angle to give us components in that direction, and we can answer. So we're going to basically take Y to be like this and X to be like this. So if we put axis on this question, this would be Y and this would be X. So now we know what X and Y direction we're going to work in, we can resolve the weight to fit in with what we've chosen. The weight must have a component in our Y direction and a component in our X direction. And once we calculate them, we're back to our square with up, down, left and right. So first of all, calculating the weight in this direction, well, we need an angle. And the angle is going to be this one, and simple geometry about dropping perpendiculars through triangles will tell you that this angle here will always be equal to this angle of the slope here. So in this case, theta is going to be 30 degrees. And our W, our weight value, is going to be 5.4 newtons. And we end up with a triangle, we end up with a situation like this. We have our X and our Y, and our resultant, which we've already got, is 5.4, this being theta, and we now resolve. And we're back to a simple question like we saw here. So let's do that stage. We're going to have to work out, this time we're not going to calculate the resultant, we're going back to the component, so we can't use these equations, we use the trigonomic identities, where we're going to find that, sorry, not f this time, wx will be equal to w either cos or sine theta, and wy will be equal to w either cos or sine theta. Now, notice how I can write this bit out without actually having to think of anything so far. Very useful to do an exam, puts you on the right path. Now I decide whether I'm going to write cos or sine, and that comes down to whether I'm looking at the adjacent or the opposite. So the first one, if we look at wx, well, wx is theoretically this line here, which is opposite. So we're looking for something that gives us the opposite in the hypotenuse, which would be part of the SOHCAHTOA, or sine theta. And we're also looking at this angle, this side here, which will be the adjacent. Convention says we could just always put the opposite to this anyway, but for just checking, we'll say this is adjacent. So after adjacent to hypotenuse, we're looking at the ka part of the SOHCAHTOA, or cos. So for x, we get 5.4 sine 30 degrees. I'll put there, which equals, when it's calculated, 2.7 newtons. And then for the y value, 5.4 cos 30 degrees, which works at 4.7 newtons. So now we have our x and y components of this force. Now we have to decide, can we answer the question? Okay, so for part 1, we're looking to answer the question of friction. Okay, so friction, we're looking at this direction here, our x component. Now, what forces do we have at play? Well, we've got friction in this direction, and we've got the component of the weight in this direction, which we've calculated to 2.7. There are no other forces in the x direction, which means if this is an equilibrium, the friction must be balanced against this, which means F is equal to Wx, which is 2.7 newtons. Then it asks us for the support force, or in this case I've labelled it the normal force, and that, we look at this again, we've got the normal force pointing upwards in the y direction, and the only other force we've got to play is the downward component of the weight, of the y component of the weight here, and therefore they must be equal and matched to each other because it's an equilibrium. Therefore the normal force, or the support force, is going to be equal to the y component of our weight, which is 4.7 newtons. Now answers question 2. Question 3. It says an archer pulls a bowstring until two halves of the string are at 140 degrees to each other, as in figure 6. Let's have a look at figure 6. There we go, the bowstring. The force needed to hold the string in this position was 95 newtons. Wants us to calculate the tension in each part of the bowstring in this position, and the resultant force on an arrow at the instant the bowstring is released from this position. So, first of all, we'll draw a simplified diagram. We'll say that we have a force of the draw of the bow of 95 newtons, which I'll call F, and that acts on two bowstrings They are 140 degrees to each other, so, and they're equal, we can say they're at 70 degrees here and 70 degrees here. That's clear on the camera. And these will be forces here and here of tension. We can call this T1, call this T2. And we need to calculate the value of the tension in the bow. To do this, we need to consider this force here and match it to this one. And the way we can do that here, so this force here, now when I say this force here, what am I talking about? I'm talking about the vertical components of these two tensions. So there will be a vertical component this way. There'll also be horizontal, but we know they'll match each other because otherwise it would go left to right, and it's not, it's going to go just backwards and forwards. So these would always work to match each other. So we've got two tensions here added together to give this, and they're both vertical components of T1 and T2. How do we write that? We can say that this force here that we can call T in the Y direction, we can call it Ty, will be equal to the Ty from 1 plus the Ty component from 2. Okay, so we can say that in maths we'll call this Ty. So we want the vertical component of this one. Now we're going to use some trigonometry here. We've got the hypotenuse, we've got the side adjacent to the angle, so we're going to be using K, or the cos function. So we can say that this part here that comes from this side is equal to T1 cos 70 degrees, and we can say that the component this side from the same convention comes from T2 cos 70 degrees. And we know that the bow is held in equilibrium while it's being held, and therefore this force here, Ty, that's the complete vertical force in this direction as a result of these two, must be equal and opposite to 95 because it's in equilibrium. So we can actually say that this whole bit here is equal to 95. We can also do a little trick of maths here. Now I'm going to not go down the obvious route of saying these are actually the same. I know they are the same. For anyone watching who says, well, if these are exactly equal, then the tension will be equally spread. But we'll take it one step further without making that assumption, so that this would work for a generic situation where they're not even. We can take out the factor of cos 70 because both this section and this section are being times by cos 70, and you end up with this. Okay, so there's a bit of maths there. So basically if you times this in, you get this times this, so it'll give you T1 cos 70 plus this times this, T2 cos 70. So all we've done is we've taken the cos 70 back out, and therefore you can say that T1 plus T2 is equal to 95 divided by cos 70 degrees, which works out to 278 newtons. Now we'll make the assumption that we can make because these are even. Because these are even, we know these must be equal, and because these therefore must be equal, this must be shared equally between them, and therefore T1 will be equal to T2, was equal to a half 278, which is 139 newtons. And like I say, that last assumption there is only available to us because this is equal. The angle is equal. It should be completely evenly spread between the two tensions. if these were not equal and the tension therefore was not equally spread, we could only go as far as here. We could say what the total was, but we couldn't divide it up at this point. Not the way we've done here. Now, we know there must also be forces in this way, but they're not really of interest to us in this example. We're only really concerning ourselves on the tension in the bowstring. We've calculated that. We don't need to then go back and calculate this. We wanted to know the tension, which we've got. The last part of the question is, when the bow's released, what is the resultant force at the moment the bow's released? Considering the maths and the thinking and the considerations that have been involved for this first section, the second part of the question is incredibly easy. If we took away this 95 Newton force here, all of a sudden there's nothing to match these two, and we'd get a resultant force in this direction, and it would be equal to the force that already exists in the tension in the wires, which we've calculated this component of it to be 95. Okay, so don't get confused in the sense it's not 139, it's 95. So we've calculated the total force in this direction from these two 139 Newton tensions to be 95. Take away this 95 that's holding it back, and we fire the bow forwards with a resultant. So this is part 2. We fire the bow forward, a resultant of 95 newtons. Okay, so that's that question. Question 4. An elastic string is stretched horizontally between two fixed points. An object of weight 4 newtons is suspended from the midpoint of the string, causing the midpoint to drop a distance of 0.12 meters. Calculate the angle of each part of the string to the vertical and the tension in each part of the string. Long-winded, but it's actually very, very similar in design to the last question. So we have a string, first of all, with a mass hung on the string. So let's draw the simple part in first. So here's our string here. This is the string. The tension, we could calculate the tensions. We could call that T1, call this T2. We've got a mass hung on the string here of 4.0 newtons. It says that they are fixed 0.8 meters apart. So we could put a mark here. So this is 0.8 meters. So fixed 0.8 meters apart. And when it's hung, this height, or the amount that it's dropped, is 0.12 meters. I don't know if that's immediately visible on the picture, but I'll read it out again if I need it. This will therefore be at right angles. That's something else we can decide. We can give this angle here the name theta, because we know it's probably going to be useful in a little while. Okay, so the first thing we need to do is calculate the angle, there we go, angle theta, that it makes to the vertical. So the angle the string makes to the vertical, this bit here. We know this is hung at the midpoint, which means this will actually be equal to this one, so we'll have a theta there as well. So we only need to work it out once. And, well, if you think about it, we just have a triangle formed here. This is just standard trigonometry. This isn't even really talking about forces and physics yet, because it's just distances we can work with. And this distance from here to here, well, this is hung at the midpoint, which means if this is at 0.8, this must be 0.4, and this is 0.12. We can use our tan to the -1 idea. This would be the opposite side over the adjacent. Okay, so this is a concept we've used previously in this video and in others in this section. We can say this is 0.4, it's opposite to the angle we want. This is 0.12, it's adjacent to the angle we want. We can use this function here and when we work it out we get an angle of 73.3 degrees, very similar to the question above. So that's part A done. Very simple, just trigonometry, just using our tan to the -1 identity that allows us to calculate theta should we have the two shorter sides. For part B, we need to calculate the tension in each part of the string. Well, we can use the same concept that we used before. There will be a vertical component of force that equally and opposite matches this vertical component of force here. Okay? This vertical component of force will come partly from this side and partly from this side, and because it's hung in the midpoint, and again because everything's stretched evenly, we know that they'll actually be equal, but they will add together to give this force. So the vertical component of T1 and the vertical component of T2 will add together to give a force here, which we can call Ty, and that force Ty will be equal and opposite to 4 newtons, the weight, which we can therefore say that 4 newtons is equal to these two forces added together. Now, using our trigonometry, we can say that as we did here, we've got this angle, we want this side and this side, it's going to be cos, and we're going to have T1 cos 73.3 degrees plus T2 cos 73.3 degrees. Again, we can take cos out as a factor and we end up with a situation of T1 plus T2 is equal to 4 divided by cos 73.3 degrees. All I've done is exactly the same as we've done up here, which works out to 13.9 newtons. And again, last jump we can make now is we know they're actually perfectly equal to each other, so we can say that T1 is equal to T2, which will be equal to this divided by 2, which the decimal places we've been given works out as 7.0 newtons rounded up. So that's the answer to question 4, and that's the end of that section.